Welcome. In this video, we'll be going over Miller's theorem, which is a theorem used to break up an impedance, which is connected between two nodes in a circuit, into two impedances which are both grounded. So let's get started. As I mentioned, we'll be going over Miller's theorem today. Miller's theorem started off as Miller effect, and it was described by John Miller back in 1920, so in the days of vacuum tubes. It was upgraded in 1972 and formalized as Miller's theorem. As I mentioned, the main purpose of Miller's theorem is to change a single impedance, which happens to be connected between two nodes in a circuit, into two grounded impedances, so that you can analyze the circuit a little easier and make some approximations for it. Common example for Miller making the use of Miller effect is the gate to drain capacitance in a transistor, which is connected between the gate and the drain node, and you want to find just the gate capacitance to ground. And so you break that into a gate capacitance to ground and a drain capacitance to ground. And so you'd be mostly interested in the gate capacitance to ground in this case. So Miller's theorem is shown pictorially here. So we have a circuit drawn over here. So this is just an arbitrary circuit, and we brought out the two nodes, V1 node here and V2 node over here. And so we just label this as the V1 node, and we'll label this as the V2 node. And we'll assume that V2 is a scaled version of V1. So if there's some sort of gain in the circuit, such that V2 is equal to K times V1. So that's where the Miller effect becomes very important. So we have this relationship here. V2 is equal to K times V1. We have an impedance, Z, which is connected between V1 and V2, and has a current I going into Z, and of course the same current is coming out because it's got nowhere else to go. And as I mentioned, these two nodes are just two nodes, V1 and V2, which have been brought out of our circuit in order to look at them individually, but there's many more things happening down below in this circuit. So now what we know is that I, the current through this impedance, is V1 minus V2 divided by Z. So we can, because we know V2 is equal to K times V1, we can write that as V1 minus K times V1 divided by Z. Now what we'd like to do is change this into two impedances, an impedance Z1 and an impedance Z2, where both are connected to ground. So we'd like the top circuit to be equivalent to the bottom circuit. To do that, we need to ensure that the voltages and the currents are the same. We'll assume that V1 remains the same as V2, which is K times V1. So we need to make sure the currents are the same. So we need to choose the values for Z1 and Z2 such that I1, the current here, is equal to the original I, and I2 is equal to the original current I. So to do that, we'll find that the impedance Z1 should be equal to the original impedance Z divided by 1 minus K, whereas Z2, impedance up here, should be equal to the original impedance Z divided by 1 minus 1 over K. So that's just stated, and now let's look at the proof for that. The proof for that is given here. We have from before that I is equal to V1 minus K times V1 divided by Z. So we have this equation here. But we also know in the second circuit that I1 here is just equal to V1 divided by Z1. So we have the second equation here. We want to make I1 equal to I. If we do that, we have that therefore this side must equal this over here. So we have this equation, now here. And we can see that we can cancel out the V1s here. And so we have that 1 over Z1 equals 1 minus K divided by Z. If we just solve for Z then, we can rewrite that and find that Z1, sorry, if we solve for Z1, then Z1 is equal to Z divided by 1 minus K. We can do the same thing for Z2, because we have that I2, the current here, will be equal to 0 minus V2 divided by Z. So we have that I2 is equal to 0 minus V2 divided by Z2, which is 0 minus K V1 divided by Z2. Again, set that equal to I, as we did before. So I2 should also equal I, and so we have that this term should equal, we have that that this term here should equal this term. So substitute that into here. We have this going in here, and this one going in here. So making those substitutions, we find that Z2 now is given by Z divided by 1 minus 1 over K. Now in the case where that impedance Z is just a resistor, then R1 would equal R divided by 1 minus K, and R2 would equal R divided by 1 minus 1 over K, as we would expect. However, in the case that the impedance is a capacitor, so in the case up here, that this is actually a capacitor in this location, rather than a resistor, then this has an impedance of 1 over S sub C. In that case, because 1 over SC is the inverse of a resistance, so C is in the denominator rather than the numerator, we find that the new capacitance C1 will equal the original C times 1 minus K, and C2 will equal the original C times 1 minus 1 over K. So instead of being divided, it gets multiplied in the case of a capacitor. So let's do a couple of examples here. So the first example, we have an amplifier with a gain of minus 10. So an amplifier with a K equal to minus 10. And this is our Miller impedance. In this case, R, it's a resistor, and its value is 10 kiloohms. And we'd like to find out what the input impedance is looking into this circuit over there. So we see a 10 kilo ohm resistor, and we think perhaps the input impedance might be 10 kilo ohms. Turns out that's not the case, and we'll see what it actually is. So by using the Miller effect, or Miller theorem, we can see that we can replace this resistor here by two resistors, R1 and R2. In this case, R1 here will equal the original resistor R divided by 1 minus K, where K is equal to minus 10, because that's the gain of our amplifier. So the gain from V1 to V2. So in that case, we'll have that it's 10K divided by 1 minus negative 10, which becomes 10K divided by 11. So it's only 909 ohms looking into it. So although we have a 10K resistor right here, the gain of minus 10 makes this impedance look like 909 ohms looking into it. And you can see this intuitively, because what happens is if I apply a 1 volt signal here, this will go to minus 11 volts over here. So there'll actually be a voltage of 10 volts. Sorry, I did that wrong. This will go to minus 10 volts over here. So there'll actually be a voltage across this of 9 volts. Sorry, I did that wrong again. There'll actually be a voltage over here of 11 volts. So when this is plus 1 volts over here, this goes to minus 10 volts over here. So there's 11 volts across our resistor. And so a lot more current flows into this than we would have expected. And it actually looks like a 909 ohm input impedance. So that's intuitively is what's going on. And if we want to find then the overall gain, so if we want to find the gain from Vs to Vout, we can now find the gain from Vs to V1, and we just have a resistor divider here between R1 and Rs. So we could find the gain of V1 is just R1 divided by R1 plus Rs times Vs, which is 0.476 times Vs. So there's actually a loss across this resistor here because the input impedance is only 900 ohms and we're driving it with a 1 kilo ohm resistor. And then we know that Vout is equal to minus 10 times V1 because we have an amplifier here shown down here. And so we have our overall gain then. So Vout is just equal to minus 10 times V1. So the overall gain is going to be Vout is equal to minus 4.76 times Vs. And the other resistor that we have over here, R2 in this case, we didn't make use of that because we assumed an ideal amplifier here. But R2 in this case will be R divided by 1 minus 1 over K, which would be the 10 kilo ohm resistor, divided by 1 plus 1 over 10, because the negative signs cancel out over here. So it works out to be about 9.1 kilo ohms, or approximately equal to R. So it did not change much. As K becomes larger, this becomes closer and closer just to 1. Now let's do a second example. In this case, we'll have a circuit that looks something like this. And we'd like to find the input impedance here. Looking into this system, we see that we have a capacitance of 1 picofarad, and we want to see what the equivalent input capacitance is looking into this, assuming this amplifier has 0 capacitance. We'll just worry about the capacitance 1 picofarad in this case. We'll assume the gain of this amplifier in this case is minus 100 volts per volt. So what we see is that the equivalent input capacitance here, the equivalent input capacitance C equivalent will be the original capacitance C times 1 minus K. K is equal to minus 100, so that's 1 plus 100. So it actually looks like 101 times C, so it looks like 101 picofarad. So the input capacitance of this circuit, even though there's only a 1 picofarad capacitor right here, the input capacitor here, C equivalent, looks like 101 picofarads. So it's been increased by 101 times. So we can see why having a capacitance across a gain stage can cause the equivalent input capacitance to be quite large if K is large, if the gain is large. And that's why, as I mentioned earlier, this is commonly used for the gate to drain capacitance, because we do have a gain from the gate to the drain in many circuits. Another example is something called bootstrapping. So this is a second example. In this case, we'll assume in this case that we have a resistor of R equals 1K. We'll put it across an amplifier that has a gain very close to 1, in this case equal to 0.95. We'd like to know what the input impedance is looking into this circuit. So if we go through the math a little bit here, we'll see that the input impedance here is equal to R divided by 1 minus K. K is equal to 0.95 in this case, so it's a value very much equal, very close to 1. So it's R divided by 0.05, which works out to be 20 times R, so it'll actually be at 20 kilo ohms. So in this case, the input impedance looking into this circuit, Rin, is approximately 20 kilo ohms, so it's 20 times the value of our 1K resistor over here. And that's called bootstrapping because we're trying to keep the current going into it almost zero. So in fact, we're trying to follow, V2 is trying to follow V1, which will make the current going into this resistance almost zero. If V2 is exactly equal to V1, then in fact it would look like infinite impedance. It's kind of holding something up by its own boots. So it's bootstrapping. You can also do this with a capacitor. If this is a capacitor of C equal to 1 picofarad, what would be the equivalent input capacitance over here? Again, with the value of 0.95 is K. So the equivalent capacitance would be C times 1 minus 0.95, which is C times 0.05, so it only looks like 50 femtofarads. So in this case here, if we can somehow get to the other side of this capacitance, so if we have access to the other side of the capacitance here, if we can drive it with the value of an amplifier which is almost equal to the left side of the capacitor, then the input capacitance of this looks only like 50 femtofarads. So another technique to reduce the input capacitance or increase the input resistance. As I mentioned, this is something called bootstrapping, which can get used in many circuits. Though you do have to have access to the other side of the component. And that ends this video. Thanks for watching.